I figured we'll have this short podcast on something new that is just reported as a nice news item in Science. It's about these flexible solar cells. So you can see the design here that you are used to seeing solar cells, photovoltaics installed as panels on top of roofs, buildings, solar farms, and so on. But here is something that is a curved thin film panel made by Heliatech, a German solar company. So this is from a wind turbine in Spain. So imagine you are producing wind energy, and then on the structure itself you have these flexible solar cells. So you can imagine that these are going to create a lot more space for capturing solar energy as opposed to just flat panels. There are many opportunities to put them on clothes, bags, military equipment, soldiers, buildings, and so on. So these transparent organic photovoltaics are incorporated into the glass facade here of the biomedical and physical sciences building at Michigan State University. A lot of research is going on, and you read it correctly here. These are organic materials, so the bonds and the structures and the uh, various um, options exist for making these more flexible than the so-called SIGs, copper, iridium, gallium, selenium kind of cells that are typically made silicon based, but then you had perovskite, which made a lot of noise because the efficiency of these so-called OPVs, organic photovoltaic cells, tend to be low as of now, even though a lot of research is going on to increase their efficiency from 10 less than 10% to maybe above 20% and so on. Perovskites can reach 24%. They are a mix of organic and inorganic materials. They have advantages over silicon for solar cells in many ways, but they use toxic materials, so there is an advantage for these organic photovoltaics in terms of reducing toxic materials into solar cells. But photovoltaics have their own limitations other than efficiency, and there are some operational issues that we have to look at here. But they also can get degraded by UV. So the advantage is that you can design them to absorb IR and allow visible to go through, which is why you can use them in buildings like this. So you're allowing light to come in and yet using the longer wavelengths to produce energy. But UV can degrade the bonds just like organic matter, including us, are susceptible to UV radiation, the ozone hole problem, and so on and so forth, right? But now there are newer methods of adding something like zinc oxide to reduce the UV degradation and extend the life of these organic photovoltaics for longer than a decade or a couple of decades, and so on and so forth. The other detail is given here compared to silicon cell, which has an anode and a cathode. So when the solar energy is captured by the material, an electron is excited, and then a so-called hole is left. So you have positive and negative poles created, and they go to anode and cathode to create a current, which is energy. Whereas when you use organic cells, the bonds between these electrons and the hole is not completely broken, so they cannot freely move to cathode and anode, and they only move a short distance before they tend to recombine and release that energy they captured from the solar cell as heat, and it can be lost. So very quickly that exciton is what is generated, has to be run through a so-called donor acceptor system, where the acceptor takes the electron and donor takes the hole, and you can still create electricity and energy. So it's a kind of a little bit more complicated process. So solar cell rivalry is then growing between the silicon cell and the organic cell. Silicon solar cells dominate the market, but new flexible thin film organic photovoltaics are surging in performance and could open up new applications. Both types of solar cells have a sandwich-like structure, which is shown in a simplified way here, but they differ in how they move charges to create an electric current, which is what is needed to get energy or convert solar energy, light, into a current and energy. So sunlight kicks electrons out of their atomic orbits. The electrons travel to the anode and then through an external wire to the cathode to run the electricity. So here you have electron being excited, being attracted to the anode, and then externally you bring it back to the hole, which is what is left behind when the electron is excited. So each injected electron leaves behind a positively charged hole, which travels to the cathode, where it recombines with the electron through this external wire, and the circuit can keep going, which is how the batteries work, for example, when done chemically or otherwise. In the organic cells, on the other hand, organic compounds hold tightly onto the electrons, so sunlight only provides enough energy to create an exciton as opposed to the separated electron and the positive hole. These are bound pairs of electrons and holes, so you can see that that exciton then has to very quickly reach the acceptor-donor system, where the two can be separately taken to the cathode and anode. So interleaved donor and acceptor materials pull the excitons apart, allowing the charges to travel to their respective electrodes. So carbon materials like fullerenes are very good at attracting electrons, so they were used as acceptors, but there are other issues with using fullerenes, and now newer materials are being designed for acceptors and donors for making the organic PVs work. So obviously organic PVs will not directly compete with solar for now in terms of all these details and complications. So their applications will be very different, maybe inside the rooms where IR can be used, or as building facades where they can serve as windows and energy units on various objects like wearable electronics and so on and so forth. So the competition between them continues. Organic photovoltaics took a big hit when perovskites came along and increased the efficiency of their light harvesting to over 20%, something like 24%. So this battle continues. The brightening prospects idea looks at a 2-decade rise in the efficiency with which organic photovoltaics turn sunlight into electricity, which is driven at first by molecules called fullerenes and changes to the film's structure, and then by better donor and acceptor materials to separate the positive and negative charges. So cell efficiency, you can see, originally died in the lab because of the very low efficiency, has had a couple of jumps and rises along the way, and expected to cross into perovskite kind of range above 20%. Of course, all the solar cells have to jump in the efficiency for us to harvest enough of the solar energy efficiently to do what we want to do, mainly to continue our lifestyle. But instead of burning fossil fuels and emitting carbon, we use these kind of renewables to reduce emissions and keep our eye on the global warming targets and so on and so forth. So that's kind of a very short introduction to the idea of organic photovoltaics, and you know the pros and cons and where they stand right now. So silicon still dominates the market. Perovskites are coming along, but they are not they are not outcompeting solars yet, and organics will not outcompete silicon. Organic PVs will not outcompete silicon anytime soon, but their application is very different, and they will begin to fill the gaps where flat solar panels cannot be fit in. Okay, so just keep that in mind, and we'll keep tracking these advances as we go along. There are other papers coming along in Nature Energy and so on, which look at how the chemical depositions on materials are being used to harvest light at various wavelengths, designer kind of wavelength matching of absorption by materials, and then again exciting electrons and doing conversion to the currents and electricity and energy and so on. So let's leave this here for now, okay?